Hello class, my presentation today is on groundwater salinization due to conventional agricultural practices. There are many hydrological problems that can be caused by the processes of large-scale agricultural operations. These include depletion, contamination, and salinization, which will be my main focus today. The U.S. is one of the top 3 farming nations in the world, with over 40% of the land being devoted to agriculture. And now of these millions of acres, most of them are devoted to one of 4 crops that are actually used to feed animals, which are corn, soy, wheat, and hay. And from a regulatory standpoint, these farms have many adverse environmental effects, but are really hard to measure because they're considered non-point sources of pollution. As I mentioned earlier, the 3 main problems caused by farming are groundwater depletion, contamination, and salinization, and we'll talk about each of these at least briefly. So depletion is probably the most straightforward problem we see from agriculture. Obviously, all this land will require a lot of water, and it's very easy to deplete aquifers if not cared for properly. Here you can see a graph from 2010 that shows how much water is used by Americans and where it comes from. And right here you can see that almost 2/3 of the water that we pull from the ground just goes to watering crops. Now this has led to over 25 square kilometers of aquifer depletion in the US, which isn't a huge problem, not yet at least, but it could be if it's not taken care of and monitored properly. As for contamination, conventional farming is a large source of groundwater pollution. The runoff from farms can cause a plethora of water problems, including heavy metal pollution with lead, cadmium, and mercury from the fertilizers, or even excess nutrients running off and causing eutrophication and algal blooms and stuff like that. Now for salinization. Groundwater salinity is a major problem facing farmers today because it can potentially render land non-arable for years and years into the future. So when we talk about this issue, conventional agriculture is both the cause and the victim. There are 3 main ways groundwater salinization is instigated. The first is messing with the root zone. Replacing the native perennial deep roots with a new homogeneous root system like corn causes increased groundwater recharge, which raises the water table. Now, when this water table raises, it allows salts from lower zones, like the regolith zone, to become mobile, and then they can get stuck in the soil and cause sodic soil. The second would be increased pumping, which is kind of intuitive, but unlike the root zone problem, which causes an imbalance in the water balance equation from decreasing the output, this actually increases the output, which creates negative pressure in the aquifers. And then groundwater from other regions, which is also carrying salt and other solutes, will move in and mess up the balance of the soil. The last is plant uptake and evapotranspiration. Now, with a large organized root system that you would have in a field, the plants are all going to absorb the water from the water table and evapotranspirate it and leave any solutes behind, which is inevitable but still a consequence. Salt-affected soils fall into various categories that are measured with pH and electric conductivity. For the purpose of this presentation, we'll be mainly concerned with saline sodic soils that have a pH less than 8.5 and an EC of less than 4 millimoles per centimeter. But there's also sodic soils, which are just low in soluble salts but high in exchangeable sodium. So there's a lot of Na. And saline, which is extreme. And that's when the pH is below 8.5 and the EC is above 4 millimoles per centimeter. Now talking about management, there are many management methods that are used to manage the groundwater salinity. These include leaching, which is adding excess water beyond what is necessary for the plants, chemical additives that pull the salt ions out of the soil, and then sustainable pumping methods as well. So the chemicals that are added to irrigation that are used for desalinization are gypsum and calcium carbonate. These two compounds work by chemical precipitation of other salt compounds. So basically, the calcium in these two compounds dissolves and then precipitate the sodium in the soil, which lowers the pH and the salinity in the root zone. So I found a study that tests the main management techniques to take care of the groundwater. And this study is called Agricultural Practices on Groundwater Salinity, that was done by D.L. Suarez in the late 90s, early 2000s. And it tests the effects of different types of irrigation management with variable leachate fractions. So he tested the leachate fractions in order to pinpoint if the salinity of the soil and groundwater was based on the quality of the irrigation water and what was in it. So this first graph shows two different leaching fractions, the 0.1 and the 0.4. And the graph measures the salinity measured in moles per charge liter over time. Now, a leaching fraction is defined as the ratio of the quantity of water that's draining past the root zone to that that's infiltrated into the soil surface. So basically, the higher the leaching fraction, the more excess water is used. Although you would expect that if the irrigation water was the cause of groundwater soil salinity, that the lower leaching fractions would lower the salt levels. Now, at first, this trend was apparent, but as time passes, the trend actually reverses, and instead, the higher leaching fraction rates actually decrease the groundwater salinity. Without any leaching or lower leaching, the salt surge from the irrigation water may never reach the water table. That is steadily lowering because you're pumping water from it. This would cause a large salt accumulation in the unsaturated zone of the water table, and which would cause salty soil. But when you add excess water, the system can, in a sense, reach equilibrium. So a certain amount of salt that accumulates in the unsaturated zone would be washed out by the excess water, and the excess water is holding the same amount of salt. So you're not increasing this salinity over a long period of time. The second graph shows water with the calcium carbonate additive. And this concentration is immensely lower, almost twice as low over a longer period of time. Now this happens because the aqueous calcium carbonate dissolves and forms a precipitate with the sodium in the soil, which reduces the ionic charge and the ability for the salt to pull water away from the roots of the plant. But there does seem to be a reduction in saline sodicity for the lower leaching rates in this case. Not a large difference, but it's definitely there. Finally, the last graph simulation from the study was with the gypsum additive. The gypsum did not seem to be as effective in the removal of salt content, even though it's still substantially lower over time compared to just no chemical additives. But this happens because the chemical formula for gypsum is CaSO4. This means that when it dissociates to bind with the Na and the Cl from the salt results in an excess of NaSO4 water. So in certain quantities, the gypsum does not effectively reduce soil salinity. Instead, it merely displaces the Na. The variation between the leachate fractions is much more drastic in this simulation, and this could be because of the gypsum's inability to deionize all the sodium ions in the soil, causing a larger accumulation over time. Gypsum is still the most common additive, though, used in efforts to reduce or remediate saline sodic soils. In southwestern regions of the United States, it is commonly deep-tilled into the fields for agriculture in order to compensate for the salt loading that will occur when they fertilize the plants. This figure did follow the first trial's pattern of early spikes in salinity with high leaching and then a level off towards the end. But this illustrates the danger of creating solutions to groundwater salinity in a short-term timescale rather than mapping out what the long-term effects could be. So as you can see, agricultural irrigation practices have a multitude of adverse side effects to the system that they also rely on for their own sustainability. So using proper leaching fractions and irrigation additives are very necessary to our food supply. Hopefully this shows how important it is to remember to consider these factors in order to be a good steward of the land and water resources that we have in order to sustainably produce food for future generations to come. And here are some of my references. Thank you very much for taking the time to listen, and I'm looking forward to any questions.